In the previous video, we talked about how to use the while loop. We looked at the two examples, right? We looked at the convergence of series, which is basically just computing this particular summation. It's a summation, right? Summation of 1 over n squared, and n goes from a 1 to a capital N. Right? When big capital N goes to infinity, the limit of this series should be pi squared over 6, right? And then we don't really know how many terms we're gonna need, right? But we know this particular criterion. So if the summation actually has reached 0.01% of the exact value, which is pi squared divided by 6, and then we know we can actually stop the iteration. So we're using a while loop, because while loop allows us to use this kind of conditional as some kind of a criterion for keep iterating, right? Once the conditional evaluates to false, then we don't have to keep iterating. Then we can sort of stop the loop, right? So that's the first example we looked at, and then the second example was this example. Right? It's again a formula for computing pi. It's 1 over pi, right? But it's got two variables that needs to be updated for each iteration, x and y. And the new value of y depends upon the old value of y, and together with the new value of x. So we need to update x first before we actually update y, right? And again, we don't really know how many iterations we're gonna need, but the criterion for keep the iteration going is this thing, right? So the absolute value of y subtract 1 over pi must be, if it's larger than 10 to the minus 15, then it's then we should keep iterating, right? But as soon as this absolute value is smaller than 10 to the minus 15, then we can stop the iteration, right? So there was the two examples we looked at when studying the while loop, right? And now let's go back to this. Let's go back to our to the first example that we used to motivate our study of the while loop, right? That's using the Newton's method. So how do we actually use the Newton's method to find the roots of a particular function, right? So the function is fx, right? We have no idea what the root actually is, but the criterion for stopping the iteration is kind of obvious, because what exactly is the root of a function, right? The root of a function is when the function actually equals to 0, right? When if we need to find the value of x so that the function value is as close to 0 as possible, right? So the criterion for stopping the iteration is the absolute value of fx is very, very close to 0, right? The absolute value of fx is smaller than TO, some kind of tolerance value, right? And then for this particular example, it's actually telling us T0 is less than 10 to the minus 8, right? So as soon as the value of the function, or the absolute value of the function, has reached is smaller than 10 to the minus 8, then we can stop the loop, right? And then another thing that we need to pay attention to is this particular updating formula. So x keeps changing from iteration to iteration, right? We need to compute the new value of x from the old value of the x, and also the value of the function at the old value of x, and then the value of the derivative function also evaluated at the value of old x, right? And then we use this, we subtract them, and then we get the new value of x. We update our x, right? And then this kind of updating formula needs to be iterated for a number of times until this criterion is reached, right? And when this criterion is satisfied, we can stop the iteration, right? So now let's write a script first. Later on, we're gonna convert that into a function, right? Once we have learned something about function handle, we can actually turn this thing into a function. But for now, let's just write a script, right? So I'm gonna do a new script. Say Newton's method for finding the root of a function, right? good. Maybe let's save it. Let's save it as f newt. Uh, let's call it 1, right? Later on, we're gonna change the version number. We're gonna do f newt 2, f newton, newton, f newton 1, f newton 2, f newton 3, and every version is gonna have a sort of a number that's kind of keeps changing, right? And then let's just save it, right? And then let's work on the code. So let's look at what kind of a data structure, what kind of containers, what are the containers we're going to need in order to actually put together this updating formula, right? Obviously, we're going to need a container that's going to store the approximations to the roots, right? Let's just call it x. And then we need to initialize it, right? We need to put some initial value into it. And this particular problem is actually telling us which value we want to start with, x0, because x0 equals to 1.5, right? X0 is the value for the first equation when n equals to 0, right? So the initial value for x is 1.5, right? And then what else do we need, right? We need two containers for storing the value of the function and the value of the derivative function evaluated at the location, right? So f. So what's gonna be f, right? What's gonna be f? We can call f cosine x. Cosine is a Matlab intrinsic function, right? Plus sine x, right? That's for storing the value of the function, and that's the container. So f is the container for storing the value of the function, right? And it's evaluated at the initial value of x, 1.5, right? So once Matlab finished executing this line, f is gonna store the value of cosine 1.5 plus sine 1.5, and then we're gonna need a container for storing the derivative function, also evaluated at the initial value 0. So it's minus sine x plus cosine x, right? So after Matlab finishes executing this particular line, the number that's going to be stored inside of df is going to be minus sine x minus sine 1.5 plus cosine 1.5. You add them together, right? And then that's pretty much all the containers we're going to need, right? That's all the containers we're going to need, right? And then we can just start to write our while loop, right? So we're supposed to give the conditional for keep iterating, right? It's not the conditional for stopping the iterating. It's the conditional for keep iterating, right? So what's the conditional for keep iterating? It's so usually when we look at the mathematical description, it's gonna give us a conditional for us to stop the iteration. So when the absolute value of f is smaller than the tolerance, that's 10 to the minus 8, right? We can stop the iteration, right? But the conditional that's behind the while statement must be the opposite of that. That's the conditional for keep iterating. So it's the absolute value of f must be larger than or equal to 1e minus 8, right? So as long as the absolute value of f is larger than or equal to 10 to the minus 8, we keep iterating. We keep doing the stuff that's inside of the while loop, right? And what's the stuff that we want to do inside of the while loop, right? The stuff that we want to do inside of the while loop is first we need to update x. We need to update x, right? We need to update x. So how do we actually update x? It has given us this particular specific formula, right? The new x must equal to the old x. The new x is indexed using n plus 1, right? But n could be any number, right? It could be 0, 1, or 2, or anything, right? It doesn't matter. But as long as the n the subscript is n plus 1, and the on the left hand side, and then on the right hand side the subscript is n, then it's a formula for us to actually compute the new value from the old value. So xn is the old value, right? Because it's from the current iteration n, and then xn plus 1 is the new new value. That's for the next iteration, right? Because n plus 1 is the new iteration number, right? And then we need to subtract f divided by df, right? So do we have f? Do we have f? Yeah, we have f. F is our container for storing the function value, right? Do we have df? Yeah, we have df. df is the container for storing the derivative function, also evaluated at the current x value, right? Both of them are evaluated at the current x value, right? So that's for updating the x. So as soon as the x is updated, we have a new value stored in the x container now, right? And then the next thing we want to do is to actually update both f and df, the value that's stored inside of the function value and also the derivative function value, right? Because now x has changed. So we need to recompute f and df. The thing about Matlab and mathematics or other kind of a computer algebra system is that you have to tell Matlab to reevaluate those functions, even though you have given the specific formula, right? But Matlab doesn't really have a memory of those specific formula. It can only remember those values, right? So the value that's currently stored inside of the f is still the old value that's computed by using the old x, right? And the value that's stored inside of the df is still the value that's computed by using the old x. But now we have updated x, so we need to update both f and df also, right? So f, we need to recompute f by using exactly the same function. Right. So that's the body of the loop has just these three lines, right? You update the x first, and then you use a new x to update f, the function value, and then you use a new x to update the derivative function value, right? And then you go back again to reevaluate this particular conditional, see if it's true or false, right? So if it's true, then you keep iterating, but if it's false, then you have to stop iterating, right? And pretty much that's the entire algorithm. There's really nothing more. But if we look at the requirement of the output, have the output of the program displayed to the command window the various quantities as shown below. So you need to know what's actually x, right? What's actually the root, basically. What's actually the root? And then you need to know what's actually the function value at the root. It's supposed to be less than 10 to the minus 8, right? Otherwise, it's gonna stop, keep iterating without actually stopping, right? So as after it has stopped, then it means that the function value must have actually reduced to a value that's smaller than that, right? And then we must pay attention to the last thing. That's after 4 iterations. So the problem actually requires to actually print out the number of iterations that we have gone through to actually reach this kind of convergence. So we need to keep track of the number of iterations. So how do we actually keep track of that? Right? We define n equals to n starts as with the value of 0 inside of it, and then inside of the loop, after we have finished the loop body, we increase n. We increase n by 1, right? And now we're done. We're done. So all we have to do is to actually display the output. Let's just using a disp. So disp we need to display this kind of text, right? So let's concatenate those strings together. Right. So at x equals 2, right? That's sort of the first string. And then what I have to do is to use a num to str to convert the number to the string, right? X is a number, and then we need to convert it into a string. And then there's a comma, and then fx equals 2. and then num to str, the value of f, right? The value of the function, that's f, right? And then after how many iterations, right? Num to str n, this many iterations, right? And that's our entire output. Okay. So let's give it a run and see if it's gonna produce the right output. So at x equals to 2.3562, that's like a rounded number. It's not exactly like that. And fx equals to 1.1102 e to the minus 16 after 4 iterations. Right? It looks almost identical, except that maybe the number of digits or the number of precision of the x is not as high as this one. Right? But it's okay. But it doesn't really matter too much. Right? So now we've got a script. We've got a script for implementing the Newton's method. Right? And but this script is has some redundant code. It's got some redundant code. It's got some redundant code. So right. And suppose we change the form of the function. Suppose it's not cosine x plus sine x anymore. It's a f equals to 2 times x, or f equals to x squared, x cubed, that kind of thing. Right. If we change the form of the function, then we have to change this line, right? This the difference has to be changed also accordingly, right? That's not a we must do that, right? But if you have duplicate codes like this kind of thing, right? If you change one place, you have to remember that you have to change another place, right? Suppose you have a quite big program. It's not just like a 16 line or 15 lines. It's like a 1,500 lines. The codes that's scattered around the entire file. Suppose you have kind of composed of multiple program files or program source codes, right? And you have this kind of code that's duplicated among all those files, right? And then as soon as you change one place, you have to change every other places, right? It becomes really difficult if you have to manage so many files and very long files, right? So it's kind of desirable to actually remove any kind of redundancy in the source code, right? So how do we actually remove the redundancy? How do we actually remove the redundancy? But let's look at the flow of the program, right? So we initialize the x to 1.5, right? And then immediately we recomputed f and df, right? Let's skip this line. Let's skip n equals to 0. Let's just ignore it for now. And then what's going to be the next thing, right? It's going to do this. It's going to evaluate this conditional. It's going to be false, right? Otherwise, it's not going to keep iterating, right? And then what's going to happen? It's going to do this updating of x. We're going to get a new value for x. And then we reevaluate f and df, right? So suppose we look at it the other way. Look at it the other way, right? Suppose we can actually put this while loop to include both lines. Can we actually do that, right? Suppose can we actually remove these two lines? Can we do that, right? Can we suppose we comment out these two lines, and then cut it, and then paste them there, right? Is that gonna work? Is that gonna work, right? Is that gonna work? So if you try to run it, it's not gonna work. Actually, it's not gonna work. Since it's a script, let me do a clear all at the beginning, right? Let me do that. Let me do that, and then let's run it. That's gonna give me a syntax error on line 7. That's this particular line. Right? It's telling me undefined function or variable f. But why is that? Why is that? Right? We have a function that's defined here, and it's got a name of f, and it's got a value here, right? But the problem with this particular piece of code is that when we execute this particular conditional, this conditional is in front of this, is above this particular line, right? So Matlab is going to execute each of the lines sequentially. It's going to do this line first, do this line, and then it comes to this line, right? When it executes this particular line, you don't really have a variable fx defined yet, and you don't really have numbers inside of it yet, right? So how do you actually deal with this kind of situation, right? How do you actually deal with this kind of situation, right? So in order for this line to make to work, let's add one more line. Right. Still, it's a duplication. This line and this line are exactly the same, right? But this line has to be there because in order for the entire algorithm to be logical, right? In order for the entire code to be sort of logically correct, it's not gonna work. Otherwise, you define f first, right? And then this line is gonna work, right? Now the iteration number seems to be off by 1, right? After it looks like it's kind of off by 1, right? Even though we removed the redundancy for like one line, that's for df, right? But still we have a problem with the iteration number not being exactly the same as the output, right? But that's also okay because you're just counting the number of iterations off by like a 1, right? But the result of the root and also the function value is still identical, right? So if you really want to sort of make the iteration number to be also identical to the output, what you have to do is to actually initialize the n to -1, right? And then if you run it again, it's still going to produce exactly the same output, right? And now the iteration number is also identical to this particular output. So for this particular line, we have removed the redundancy, right? We now have just one line that actually computes the derivative, right? But for this line, we still have to sort of duplicate it at least once in order to actually get the code to work, right? This is less than ideal. It's not as clean, or it's not as as good as we want it to be, right? But now let's think about it, right? Let's think about it. How do we actually remove redundancy even further, right? How do we actually make our code applicable to a wider range of problems, right? So this particular script is only gonna work for this particular function, cosine x and sine x, right? And then its derivative is minus sine x plus cosine x, right? So suppose fx is changed to say x squared subtract 2, right? Suppose we change the form of fx, then we still have to make changes to the code, right? We have to change this line, we have to change this line, and then we have to change this line, right? There are three lines we need to change, right? And it's not gonna sort of automatically know how to evaluate the function or how to evaluate the derivative function at any arbitrary x location, right? So how do we actually generalize this particular function? Generalize this particular script into a function, So now let's try to um, write a function that's gonna sort of implement the Newton's method. So function, let's create a new function, right? Let's call it f Newton 2, right? And then the output arguments x is supposed to be the root, right? It's supposed to be the root, and then y, right? Y is supposed to be the function value, right? And then maybe the number of iterations, let's say n, right? If we want to know what the iteration number could be, right? And then what's going to be the input arguments, right? Let's look at our script. What's the input? We need to actually know what's actually the starting value for x. What's going to be the initial value inside of the x, right? And then we need to know what's actually the function f, and then what's actually the function of df, the function itself, and then the derivative function, right? That's the two things that we need to know. And for now, let's just think about the initial value x0 as the input, right? Let's just put this x0, the starting value for x, as the only input, right? And later on, we're going to look at how do we actually use f and df as two input functions. It looks like f and df are just the two values, right? F is a value, that's a tuple, right? Df is also just the value of a tuple, right? But when you actually try to write a function like this kind of thing, right? The f and df must be computed either inside of the function, or it must be supplied in a way that's kind of dynamically changing with the value that's chosen inside of this particular function. Do you see the problem? Right? Do you see the problem? So the Newton method function f Newton 2 this function itself must know the form of the function and the form of the derivative function. Otherwise, it won't be able to actually compute f and df based upon the value x that has already been chosen, that's automatically chosen inside of this particular algorithm. So what exactly is the next x is not sort of determined outside of the function. It has to be determined inside of the x function, right? Except for the initial value for the x. The initial value of the x is supplied to the function as an input, but all the x values, all the rest of the x values must be determined dynamically based upon this particular Newton's method algorithm, right? And then because only this particular function f Newton 2 actually knows what's going to be the next x value. So if you want some outside function to supply those f and df to you based upon this kind of a x value that's computed inside of this f Newton 2 function, then those outside functions must be able to know what are those x values that's determined using Newton's method, right? That's kind of a very difficult thing to do, at least for now, right? But if we do not choose that route, we must know the form of the function inside of this particular function, inside of the f Newton 2 function, right? We must know how to actually compute those function and derivative function. Otherwise, we won't be able to actually determine the f and df values inside of this function, right? So let's, before we worry about that, let's just assume that we know the function form. That's cosine x plus sine x, right? Let's assume that. So x equals to x0, right? And then n is going to equal to so what am I going to do? So let me not worry about the iteration number first. Let me not, oh, maybe I still want to do that, right? So let's still n equals to -1, and then f is gonna equal to cosine x plus sine x, right? And then while abs f smaller than larger than or equal to on e minus 8 10 to the minus 8, and then and right, and then what, and then f equals to cosine x plus sine x, and then df equals to minus sine x plus cosine x, right? And then x is gonna equal to x subtract f divided by df, right? Did I get the formula right? And then n equals to n plus 1, n equals to n plus 1. Let me save it. And then in f new to 1, I can actually just replace this whole thing with just a function call, right? X n xf n is gonna equal to f Newton 2 1.5, right? If I run it, oh, it's saying that y is not as okay, y, it's not y, it's f, it's not y. Let me save it and then run it again. Right, so the result is still correct. So it means that the function is correct. The function is correct, right? But now suppose we want to change the form of the function. We don't want to use this particular function anymore. We want to change it to say x squared subtract 2. Right? Let's comment out this one. X squared subtract 2. Right? And if we do that, we must also change this line also, right? X squared subtract 2. And then we also have to change the derivative function, right? That's 2 times x, right? So suppose we do that, right? We do that, and then run this code. So this is after 3 iterations, it has reached this particular value of x. 1.4 square root of 2 is 1, right? That's a square root of 2, right? So it looks like the value is correct, right? But it becomes really tedious, right? So suppose we want to compute the root for function x cubed subtract 9 or something. So every time we want to apply the Newton's algorithm on a new function, we have to change the source code of this particular function, right? And it's error prone, and it's very difficult to maintain, right? So how do we actually make this function more applicable? How do we actually do that, right? In the ideal case, that is that the function itself can be used as inputs, right? The form of the function, I mean not the value of the function, right? The form, if the form of the function, like this kind of thing, can be used, and also the form, this particular mathematical expression for the function and the derivative function can be used as a input to this particular Newton's algorithm, then it becomes very flexible, right? All we have to do is to actually define those particular function forms, particular function expressions, and then we can just pass them in as inputs, right? And the Matlab actually provides a mechanism for us to do that, and that mechanism is called function handle. It's called function handle, right? Now suppose we define a function. Let's write a new function that's going to encapsulate this particular expression. Let's just do that. Let's create a new function. Let's call it um, f Newton func uh, function function, right? And then it's gonna take an input, that's x, right? That's x, and then it's gonna give us an output. Let's call it a y, right? And then y is gonna equal to x squared subtract 2, right? That's pretty much just our function, right? That's pretty much just our function. Let's save it, right? And then this function has a name, right? This function has got it's got a name. It's got a name, right? So, but what does this name actually mean, right? What does this name actually mean? For now, it's a function name, and when we try to actually use this particular function, we have to use this name, right? We have to use this name to actually call this function and give it an input, right? But what about this particular function itself? What about this particular text file that's used to define this particular function? What about this particular mathematical equation that's used for computing the output from the input, right? So when we actually call this function, all it produces is just the output based upon the input it's giving it. But the function itself has no representation to it, right? But now what do we want? What do we want inside of this particular function is a function, is a representation of the function itself. It's not really the value of the output of that particular function, right? Suppose x has a value of 2, then 2 squared is 4. 4 subtracted 2, that's 2, right? The output is 2. So if you want to know the output of this particular function based upon the 2 input, based upon the input value of 2, then we call this function, right? But now what we want to do is not really to call this function because we have no way to call it. We don't really know what's going to be the input. The input is always going to be determined inside of this fnew2 function, right? So what we want as input is not the output value of this particular f Newton function. What we want is this particular expression, the definition of this particular function, right? We want this function itself. We don't want the function. We don't want the function output, right? So how do we actually do that, right? How to actually do that? So there's a mechanism in Matlab that allows us to actually to retrieve some kind of data representation of a particular function, and it's called function handle. It's called function handle. So now we have this particular function, right? We have this particular function. We have its name, right? If we want to call this particular function f Newton function, and then we give it some kind of input, then it's going to give us an output, right? The function itself can be used like that, right? But how do we actually come up with a representation of the function itself? Right. Let's call it h. H equals to at. Right. So now h is what? H is defined as this particular thing, right? And then what this particular thing actually looks like is the at symbol. This at symbol appears in all the email addresses. You have to use the at symbol. You have to hold down the shift key and then press the number 2 on your keyboard. Then you get the at symbol, right? And then followed by the name of the function, right? And then if you do that, you're gonna get something that's called a function handle. And then the function handle is assigned to a new variable that's called h. And Matlab is actually telling you h is equals to what? Equals to a function handle. It's a data type, and the value that's inside of it is called f Newton underscore function, right? So this is actually a link. If you want to click on it, it's gonna open up some kind of a help page to tell you what the function handle actually is. But for some reason, maybe the help page is not installed or something. It's not showing up. Oh, now it's like it's giving me something. Okay, so now it's giving me something, right? So it looks like a foreign name, right? Something that you haven't heard before. What exactly is a handle, right? What exactly is a handle to a named function, right? What does it mean, right? What you can think of is that the handle to a function is a data. It's just like a number, right? It's just like a number, a string, that kind of data, right? But the thing that's stored inside of this kind of data structure or this kind of container is not exactly a number or a string. It's a definition of the function. Right? It's a definition of the function. It's not the output of the function based upon certain input. It's the definition of the function. So you can think of h as sort of the expression as this thing, right? And the nice thing about this kind of a syntax is that you can still use h just like the function, right? So if you give h a input with the parentheses around it, it's still going to compute the output, and it's going to give you the correct output based upon that particular expression, right? So 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 if h is actually a piece of data, then you can pass it. You can pass it into a function, right? You can pass it into a function. So let's change the first input to h, right? Change the first input to h, not f, h, right? Let's call h. H is the first input, right? And then because h is going to encapsulate the expression for that particular function, then we don't really have to call this function value anymore, right? We can comment out this line. So what we can do is actually to use f equals to h x, right? Or what we can do is just to get rid of this line. Get rid of this line altogether. And just when we actually need to use f, we just call hx, right? And then we can completely get rid of this line, right? Because the reason that we need this f container was just because the expression could be quite long, right? The expression of the function could be quite long. For example, cosine x plus sine x, you have to type a lot of things. So that's why we come up with the container f to store the value that's coming out of this particular very long expression, right? But now we're treating h as a function handle now, right? And it's just a one character. So hx, that's not too long, right? It's just a like a 1, 2, 3, 4, 4 symbols. Then you get the function, right? And then we also don't need we don't need this line either, right? We can just replace f with hx, right? We don't really need this line. When we need f, we just replace it with hx, right? But for now, we don't really have a function handle for df yet. But later on, we're gonna also change that. We're gonna change that too, right? And now let's save this particular function. Save this particular function. And then let's go back to our script and yeah, let's just it's gonna require one more input, right? So what's gonna be the first input? What's gonna be the first input? Right? What's gonna be the first input? So h must equal to at f Newton function, and then we give h as the first input. Right? You don't have to call it h. Let's call it fh, right? Fh, and then we use fh as the input, right? And then this fh is going to be copied over. The value that's stored inside of this fh container is going to be copied over to h when we call that function, right? So now let's rerun it. F is the output. Okay, so I still need to sort of, so I use the f as the output. The it's actually supposed to be the final value of the function after we have finished this kind of all the iterations, right? And then that's gonna be the output. So what I have to do, so that's a variable. So you cannot just replace this one with hx. You have to actually define a f equals to hx, right? And now let's run it, right? So the square root of 2, that's 1.421. So that's good enough, right? And then we can just replace n because there's no index offset now. So we don't really have to. There's no index offset, so we don't have to start from -1 anymore, right? And now we have to sort of try to. So this is a function handle, right? And then we also need a something to represent the derivative, right? Matlab can compute derivative analytically for you if you have installed the symbolic toolbox, right? So for any kind of complicated function, you can sort of try to ask Matlab to actually compute its derivative expression for you, right? So that's similar to doing calculus. Right? In calculus, you have to compute the derivatives by hand, but Matlab or Mathematica, if you know how to use the software Mathematica, then it's also a very convenient tool for you to actually uh, uh, get the derivatives, right? So now let's look at how we can actually get rid of this particular line, right? In this case, we're going to require another function handle input. Let's call it dh, right? Let's call it dh. Um, and then we can just get rid of this line, right? So whenever we need df, we just replace it with dhx, right? And now outside of the function, when we actually try to call this function, we have to sort of give it a new function handle, right? dfh. Let's call it. We have to define a new function now. We have to define a new function now, right? So that's the form of the function, right? That's the form of the function. But now we have to define another function. We have to define another function. That's gonna be used for storing the definition of the derivative. Let's call it f Newton d function. Right? It's still gonna have an input that's x, and then it's still gonna have an output that's called y, right? And then for this particular function, they were using its analytical derivative is 2 times x, right? So y is gonna equal to 2 times x, and then let's save it. So now we can define our dfh. That's at f Newton d function, right? And then dfh. And then let's run it again. Right. So by now our function has become quite different from the function that we started with, right? Let's write some descriptions about this function. So h function handle pointing to the function definition file, to the function definition. That's probably good enough. And then dh function handle pointing to the derivative function definition, right? And then let's get rid of this line, and then get rid of this line, these 2 lines, right? We don't really need those 2 lines. And then maybe x0 starting x value, and then x root of the function, and then f value of the function at the root, and then n number of iterations needed to reach the root, from the starting value x0. I just put it on the like one line, yeah. So now we have our own function for we have our own function for solving the Newton's method, right? For using the Newton's method to find the root of to find the root of an arbitrary function, right? So this function is going to take function handles as inputs. So the first input is going to be the handle to the definition of the function itself, and then the second input is going to be the function handle pointing to the definition of the derivative function of this particular function handle, and then that's how we can actually use this particular function. So we need to write the two functions first, and then define the two function handles, right? And then give these two function handles as the inputs to our Newton function, right? F Newton 2, right? And this is probably a good time for me to stop, right? So in the next video, we're going to talk about anonymous functions, right? And how we can actually generalize even further, right? How do we actually abstract even further, actually? So for example, for now, the function definition, it looks like that, right? We have a constant here. Suppose the equation that you want to solve is not x squared subtract 2, it's x squared subtract 3, right? You have to either actually modify the definition of this function, right, or do something else, right? Modifying the definition of the function is like a undesirable thing, right? But can you actually change this number to a parameter, for example, right? Suppose it's a parameter, and then you use a as input, right? But what's going to happen now? Right? What's going to happen now? So f Newton underscore function, this particular function, was used inside of this function as h, right? And then this function is actually calling that function, calling this function. So f Newton 2 is actually calling f Newton function in a very specific way. It's calling it using h, right? And then how many input parameters is it giving it? It's giving it just one input parameter, x, right? It's not giving it two input parameters, but the definition of the function actually requires two input. One is x, and then the other one is the parameter of that function, that parameter that's used for defining that function, right? So here you're gonna get a syntax error. Right? But the person who's writing this particular function doesn't really know how to actually call this particular function, so it's actually making an assumption. It's assuming that it only takes one input, right? And then even if the person who's writing this f Newton 2 function knows that this particular function is going to take two input, it still doesn't have the person still doesn't have any idea about what's the appropriate value for that second input, right? It doesn't really know what's supposed to be the a, right? A is supposed to be supplied by the person who's going to use f Newton 2, right? So how do we actually solve that kind of problem? But this video is probably too long for. It's probably a good idea for me to actually stop and we'll continue our discussion about function handles in the next video.